Okay, so in this video we're going to talk about our next type of Newton's second law problem, and these are pulley problems. And these pictures both show an example of what a pulley is. It's basically where you have objects connected by a string, and the string runs over this circular thing, which is free to rotate. We're going to assume, just for the sake of simplicity, that when we're doing problems with pulleys, that there's no friction anywhere in the pulley. There could definitely be friction along the surface if an object is touching a surface, but there's not going to be any friction in the pulley itself. And we're also going to assume that these objects are connected by a rope or a string which has no mass, and that the tension everywhere along the rope or string is the same at all points. Okay, so here is how you approach a pulley problem. Now, all second law problems have the same basic process for solving them. You draw the FBD, you write out your second law equations, you determine acceleration, and then you write down the sum of the forces before you plug in any numbers. Okay, but pulley problems have a trick to them, and the trick is that we're going to use a slightly different coordinate system than we usually use. Okay, and the coordinate system, it's a little confusing to understand at first, but once you get into it, it makes complete sense. Basically, we're going to establish a coordinate system where instead of up, down, left, and right, instead of those being our classic directions that we think of, we think of which way the object is accelerating, whichever direction the object is, that should say accelerating, not acceleration, whichever way the object is accelerating, either clockwise or counterclockwise, we make that direction the positive direction. Okay, and so when you're doing a pulley problem, you have to think in terms of clockwise or counterclockwise forces. Okay, so whichever way the object is actually accelerating, you make that direction the positive direction, and then you go from there. And this is a completely different concept that we're used to, because we're not saying left or right is positive necessarily. We're talking about clockwise or counterclockwise. Now, what does that mean exactly? Well, what I mean, for example, is if you look at this picture on the left, if we were just to put these two blocks out there and let them go, we all know what's going to happen, right? The one on the right is going to fall down, and the one on top of the table is going to get pulled to the right. Okay, it's definitely not going to go the other way. And so in that case, I would say that this system is going to accelerate clockwise, meaning that any forces which serve to make the object move clockwise, we treat those as positive forces, and any counterclockwise forces, we would treat those as negative. So for example, if I think of the FBD for this situation, let's just say there's no friction, for example. I'm going to call this big object, I'm going to call that M1, and the small one over here, I'm going to call that M2. Okay, just to be able to call it something. Okay, so the FBD for this, if there was no friction, I would have Fg1 going down, that's the force of gravity for object 1, and I would have Fn going up, and then because there's a rope or string, there would be tension going to the right, and I would call that Ft. And based off of what's on the slide, the tension everywhere in the string is the same. However, when I draw the FBD for box 2, that tension is going up instead of to the right like it is for this object. So that would be Ft, and then there would be Fg2 going down. That's the force of gravity for object 2. Okay, now, what do I mean by clockwise or counterclockwise forces? Well, I mean Fg2 is making the system move counterclockwise. So Fg2, I would say that is a positive force. Okay, because this object is going to fall down, that's going to make this object move to the right. That is a clockwise force. This Ft right here, I would say, is a negative force because it's going counterclockwise. This Ft right here is also making the system move clockwise, and so I would treat that as a positive force. And these other two forces, I would just use a normal coordinate system for that. Okay, likewise, if you look at the situation on the right, we know that this is a 3 kilogram box, this is a 5 kilogram box. Obviously, the one that's heavier is going to win. And so we all know that this, if you put these two boxes on the pull-in and you let them go, the heavier one is going to fall down, the lighter one is going to get pulled up, and so the whole system is going to accelerate clockwise. But if I switched the 5 kilogram and the 3 kilogram box, then it would accelerate counterclockwise. Okay, and so based off of which forces are clockwise or counterclockwise, use that to establish your coordinate system. Okay, notice also that we now have, for the first time, two objects. And so when we're solving these problems, you have to apply Newton's second law for both objects. Okay, so let's do some examples. Pause there if you need to add that to your notes. Okay. And these are just some general steps for solving second law problems with pulleys. Go ahead and add these to your notes, and I'll talk through them really quickly. When you're doing second law problems, of course, you have to write down the second law equations for both objects. Okay, and it's really important that you pay attention to the signs of the forces. In the last example, when I was talking about how this Ft would be positive because it's clockwise, and the other Ft was negative because it's counterclockwise, when you write down the second law equations, you have to include that sign, and I'll show you what I mean in just a second. Okay, let's see. Two objects connected by a pulley must, I misspelled must have the same acceleration if they are to move together. And generally speaking, anytime you have two objects in a problem, they have to have the same acceleration, because otherwise, if one of them was accelerating faster than the other, then the string would either like stretch or it would become slack. Okay, so objects connected by, well, objects connected in any way, whether it's a pulley or not, have to have the same acceleration. Keep that in mind. Okay, that's really important to solving these problems. Okay, so generally speaking, because you have two objects in a pulley problem, you end up with more than one second law equation. And because you end up with multiple equations, you end up with what's called a system of equations. And there's two primary methods of solving a system of equations that you should have learned in algebra before. Those are substitution and elimination. And as we'll see, in most problems, elimination is definitely the easier of the two methods for solving our system of equations. Okay, so pause here. Everything on this slide is crucial to solving pulley problems, so make sure you add all of this to your notes. And let's do some examples. So we're going to do, I think, at least three examples so that you understand how to do pulley problems. Okay, so example 1. So we are given the setup shown on the right, and it says to find the acceleration and the tension. Okay, and we want the acceleration of both masses, but of course if they're connected by a pulley, then they have the same acceleration. Okay, that was on the last slide. So, like any second law problem, you always start with the FBDs. And just to give these things a name, I'm going to call this one M1, and I'm going to call this one M2. Okay, this setup, by the way, is called an Atwood machine. If you ever see that term, Atwood machine, they use it a lot in AP physics problems. IB doesn't usually call it an Atwood machine, but that's what it is. So the FBD for the box on the left would look like this. We have FG1 going down, and we have FT going up. Now, how do I know FG1 is bigger than FT? Well, it's kind of common sense that since this one is heavier, it's going to accelerate counterclockwise. So I established a coordinate system whereby counterclockwise is the positive direction. Now, if I switch these two masses, then I would have my coordinate system going the other ways. But that's just based off of which way I think the object is going to accelerate. And for mass 2, I have the exact same tension going up. Same Ft, but now this Fg is smaller. Okay, so there's my FBD. Now what I'm going to do is I'm going to write out Newton's second law for both of these objects. And so I'm going to start with mass 1. Okay, I have F net equals ma. Okay, m1ay. I determine the acceleration of the object. Is the object accelerating? Yes, definitely. So m1 is 1.8, ay is my unknown, and now I write down the sum of the forces. Okay, taking care to take into account the direction of my forces. Now, because my coordinate system, I've established that counterclockwise is a positive direction. That means all forces that are counterclockwise I must treat as positive. Okay, so Fg1 is actually going to be a positive force. So when I calculate Fg1, I have to make sure to plug that in as a positive. Yes, I know normally when you plug in the acceleration due to gravity, you end up with a negative. That's just because you're using -10 for the acceleration due to gravity. But in this coordinate system, in this case, it's not going to end up being a negative. It has to be put in as a positive. I'm also going to put in minus ft. This minus is to indicate that this ft I'm treating as a negative force because this is a clockwise force. You have to make sure to include this minus here. So normally I would write down the sum of the forces. I would just do Fg1 plus Ft. But I know right away that Ft is going to be a negative because of the direction. And I have to include that for reasons you'll see why in just a second. Okay, so this is my first second law equation. I could find Fg1, I'll do that later. But let's do M2 for right now. I do the same thing for mass 2. F net y equals m2ay. Is the object accelerating? Yes. The mass is 1.2. There's a y. I write down the sum of the forces, and on this object, remember, counterclockwise forces are positive, which means that when I do the sum of the forces, the ft here, which is counterclockwise because it's making the whole system accelerate counterclockwise, is a positive force, and then Fg2 is going to be a negative force. Now, notice what I end up with. I have Fg1 minus Ft equals 1.8 ay, and I have Ft minus Fg2 equals 1.2 ay. This is a system of equations. I have two equations and two unknowns. Now, it looks like I have more unknowns, but Fg1 and Fg2 I can easily calculate. My unknowns in this case are Ft and ay. Okay, but luckily notice that this equation is perfectly set up to solve using elimination. And the way elimination works is I'm basically just adding one equation to the other equation. So when I add this first equation to the second equation, what happens is I have negative ft plus positive ft. And so when I add those equations together, those two both cancel out. And so I end up with Fg1 minus Fg2 equals, and remember I'm just adding the top equation to the bottom equation. These are like terms now. 1.8 plus 1.2 is 3, and so that would be 3.0 ay. Okay, and now at this point I can very easily solve for ay. I need to find Fg1 and Fg2 really quickly, but then all I have to do is divide by 3 and I'll have ay. So Fg1 is going to be 1.8 times 10 meters per second squared. That's 18 newtons. Now, why is it a positive 10 and not a negative 10? Again, because of our coordinate system. This 10 is just the acceleration due to gravity that we've always used, but I'm putting it as a positive now because of our different coordinate system. Fg2, on the other hand, I'm multiplying by negative 10, again because of our coordinate system, and so that would be negative 12 newtons. Alright, so what do I end up with? I plug those values into my equation right here. I will do this up here. I have 18 minus 12 equals 3 times ay. Somebody is going to ask at this point, by the way, shouldn't I be subtracting negative 12? No, this negative sign is to indicate that Fg2 is negative. Okay, so I'm not double subtracting, if that makes any sense. Like Fg2 should be negative 12. And so when I wrote this equation down here, what it really should have been is Fg1 plus Fg2 because it's the sum of the forces. But I've already taken into account that Fg2 should be negative, and I don't need to do that twice. Okay, so that's why it's not 18 minus negative 12. It's 18 minus 12. The way I have it here is correct. Okay, so that would be 6 equals 3 times ay. Ay is going to be 2 meters per second squared. And now that I have ay, I can easily find ft by just plugging back into one of my other equations and solving for ft. Okay, so here is one of my two answers. And I can solve for another one. Let's say I plug in ay to the second equation down here. Okay, so I'm running out of space here, but ft minus FG2, which was 12, equals 1.2 times 2. Okay, I'm just plugging in AY into the second equation, so 1.2 times AY, 1.2 times 2. And then I just need to add 12 to both sides, and I get, let's see, what is that? 14.4 newtons. Okay, and they both have the same acceleration and the same tension of the rope, and so I'm done. Okay, so pause there. This is definitely the easiest type of pulling problem you could ever see. It seems like a lot, but once you get the hang of it, it's super easy to do this type of problem, the basic Atwood machine problem. You can pause there and make sure you add that to your notes. Okay, so let's take a look at example 2. Alright, so example 2 says, in the box shown to the right, box M1 has a mass of 100 kilograms, box M2 has a mass of 50 kilograms. The 4 kilogram box is falling at a constant velocity, which is at a constant velocity, of 4 meters per second. And we're asked to calculate some things. Before I even look at the question, I'm going to write out, or I'm going to follow my second law process just to get that out of the way. So M1, I'm going to draw the FBD. That would be FG1. I have a normal force because there's a surface. I have tension because there's a rope or string. And I know there's kinetic friction just because I kind of peek ahead and I see there's something about friction down here. So let's say there's kinetic friction to the left. And actually, reading it more carefully, if the falling object has a constant velocity, that means there is no acceleration, which really means that neither object is accelerating. Because remember, connected objects have to have the same acceleration. And so if M2 is falling with a constant velocity, M1 would also be moving with a constant velocity. So let me draw the FBD to reflect that. FT should really be the same length as FFK. Then mass 2, I have FG2, and I have FT going up, and those should be drawn the same length. I think I messed that up, but they should be the same length because it's falling with a constant velocity. So I write out my second law equations. Now, in this case, for mass 1, I have F net x equals M1AX. Okay, is the object accelerating in the x direction? No, because the box is falling with a constant velocity. M2 is falling with a constant velocity, which means M1 is also moving at a constant velocity, which means it is not accelerating in the x direction. I write the sum of the forces, and so I am going to have to choose one direction to be positive. I know that the object is moving clockwise, and so I'm going to choose that direction to be positive. And so I have Ft, this Ft would be positive, minus FFK, that FFK is negative, because it would be a counterclockwise force. And then, technically speaking, I also have an F net y equation, which I'll come back to later, but F net y equals M1AY. It's definitely not accelerating in the y direction no matter what. And so that's going to be 0. And then I just have Fn plus Fg1, just like I normally would. Those have nothing to do with the Pulley problem. That's just like a basic second law problem right there. For mass 2, I do the same thing. F net y equals M2AY. Is the object accelerating? No, because it's moving with a constant velocity. Fg2, though, is positive because of my coordinate system, and this Ft is negative because this Ft right here would be a counterclockwise force. And so here's my system of equations. I have one equation, two equations. Okay, so I have Ft minus FFK equals 0. Fg2 minus Ft equals 0. Notice I haven't even looked at what the question is asking. I'm just following the same basic process for any second law problem that I would be doing. Okay, so now that I wrote down the sum of the forces, now I can actually look at the questions. First question is asking me to find calculate the tension in the string. Okay, so I'm looking for Ft. Now the top equation doesn't really help me because I don't have FFK, and I can't find FFK because I don't have the coefficient of friction. But I can use the bottom equation to find Ft right away, right? Because you know, Fg2 minus Ft equals 0. That means those two forces have to be equal, and I can find Fg2. Okay, so this problem is actually easier than a normal Pulley problem would be because of the constant velocity bit. Okay, so what would that be? Fg2 would be m2 times g, so that would be 50 times 10 meters per second squared. Notice I'm making that a positive 10, not a negative 10 because of my coordinate system. So that would be 500 newtons, which means that Ft is also 500 newtons. I can immediately see that from this bottom equation down here. Okay, so the tension is 500 newtons. Ta-da! But guess what? That means FFK is also 500 newtons, right? Because Ft is also equal in magnitude to FFK because of this equation right here. So FFK is also 500 newtons. Okay, so even though this is a Pulley problem, I've tried to make it a pretty easy one because just because it's this example 2. FFK is 500 newtons. Now I'm asked to find the force of friction. Okay, I just did that, 500 newtons. Calculate the coefficient of kinetic friction between the 100 kilogram box and the table. So now that I have FFK, I know FFK is equal to mu k times Fn. And so I have FFK. They're asking me to find mu k. And so now it's just a matter of finding Fn. But I can do that all day because I've done those types of problems many times before. Fn is just balanced out perfectly by Fg1, which, by the way, is a negative force because the counterclockwise, clockwise coordinate system thing, that only applies to like Pulley problems. Fn and Fg1 you treat just like a normal second law problem. And so Fn is going to be equal to, let's see, Fg1 is 100 kilograms, so that would be negative 1,000 newtons, and so Fn would be 1,000 newtons. We have FFK, that's 500, and so mu k is going to be, let's see, times 1,000. So mu k would be 500 divided by 1,000, which is 0.5. And that is it for example 2. So pause there, make sure you add that to your notes. Okay, so example 2 is still a pretty basic second law problem with Pulley situation, but hopefully you're starting to get the hang of it. Okay, so I want you to take a peek at example 2.5. See if you can do example 2.5 on your own. Okay, it's the exact same picture, but now I've made it so that there is acceleration and there is tension. So pause it here, and I will put the answer up on Edpuzzle so you can check for yourself. But you should be able to find the acceleration and the tension in the two strings. Okay, so make sure you follow the process just like you should. In fact, I would always recommend you follow the second law problem solving process before you even look at the question, just so you make sure you get all the equations set up. This time you do end up with an actual second law, or an actual system of equations that you have to use elimination to solve. So it's a little bit more involved than the last one, but the setup should be very similar to the last one you did. So see if you can do example 2.5 on your own. Okay, so hopefully after watching this video you have a better understanding of how to approach Pulley problems. It is a little different having two objects instead of one, and it is a little different having a coordinate system where you have clockwise or counterclockwise direction as positive or negative. But as long as you understand how the process works, these problems are not super difficult. Okay. As always, please let me know if you have any questions, and I'll see you guys in the next video.